All right, logic design, digital logic design. We had come up to the binary number system. All right, so today let's look at examples on how we can convert from decimal to binary and binary to decimal. Now 306. Did anyone have any questions about the material so far? Okay. All right, so if we have a decimal number and we want to convert it to binary, this is the process. We divide by 2. Until the quotient is 0. Okay. So let's say we start with the number 343 in decimal. 343 in decimal, so subscript of 10. Divide by 2, we get a quotient of 171, remainder of 1. We note that as the least significant bit. Okay, least significant bit. So reading from right to left. And 171 divided by 2, 85. Again, we have a remainder of 1. That goes to the second. Keep on dividing by 2 until quotient is 0. Then we read the number in the reverse order. As I said, this is the MSB. And this would be the LSB, least significant bit. And 343 is 101, 01, 111 in binary. Okay. Again, we stop when the quotient equals 0. Okay, so that's from decimal to binary. For binary to decimal, we multiplied. Decimal to binary, we divide. This is a reminder right here. Okay. Then there is some math implementation. For decimal places, we multiply by 2. So if we are starting with was there any question before I move on? Okay. If you have a decimal place, let's see if you want to go from 0.392 decimal to binary, we multiply by 2. Result is here. We take the fraction, which is 0.784, and we again multiply by 2. Okay, it's the answer. It goes here. And then we read from top to bottom. We keep multiplying until we reach the desired decimal numbers or decimal places. So if you wanted like 3 or 4 decimal places, we'd go 1, 2, 3, 4. Here we are showing an example of 6 decimal places. So we want to go from 0.392 to binary. First step is to multiply by 2. From there, we get 0.784 or 0.784. 0 is brought here, 0.784. Actually, I should not write this. 0 is brought there, and the 0.784 is further multiplied by 2. The result is 1.568. 1 is brought over here. 0.568 is multiplied by 2 again. 0.568 times 2 gives us 1.136. 1 is brought here, and 0.136 is further multiplied by 2. We keep going on with this process until we reach the desired number of decimal places in the binary. Yes. So the question being asked is, if we want it to be exactly equal to the decimal spots, would we keep going until we get to 0? Yes and no. Because in the decimal, we only have 3 decimal places here. And here we have already exceeded in the binary. We have gone up to 6, twice as much. So again, we keep going until we reach the desired value. We can keep going. I haven't gone further than this. I mean, that's the example in the books. I haven't gone, but it'd be good, interesting to see how many decimal places we could go to. Okay. But does that make sense? Yes. So here, yeah, so we'd get 343 by 2 would be 171, plus 1 would be the remainder, right? 171. So the question being asked is, how do we actually get 1 here, right? So if we divide by 2, let's do it the other way around. 171 times 2 gives us 342. 342 plus 1. So 343 better to put it this way. 343 would be equal to 171 times 2 plus 1. So remainder, so if we do the long division method, we put under the window, then be 342, remainder of 1. Does everyone understand that question being asked was? Normally, if we divide, we'd say like 0.5, right? The actual answer would be 171.5, right? That's the question that was being asked. Binary number addition. If you add 0 plus 0, sum is equal to 0. 0 plus 1 gives you 1. 1 plus 1 gives you 0. 1 plus 1 plus 1 gives you 1. Then there is a carry. If you have 0 plus 0, the carry is 0. 0 plus 1, carry is 0. 0 plus 1 would be the same as 1 plus 0. Okay. So again, 0 plus 0 is 0. Carry would be 0. 0 plus 1 or 1 plus 0, the sum would be 1. Carry would be 0. 1 plus 1, carry would be 1. Sum would be 0. And then 1 plus 1 plus 1 gives you sum and carry as 1 and 1. Okay. And if you think about it in the decimal system, we get the same answer. 0 plus 0 would be 0. 0 plus 1 should give you 1. 1 plus 1 should give you 2. Which in binary is 0, 0, 0, 1, and 1, 0. These are just some of the rules that we have to keep in mind when we perform digital logic systems. And in binary subtraction, machines, or more appropriately, electronic devices, cannot perform subtraction directly. So we use alternative methods to perform subtraction. Okay. There are two methods known as ones complement and twos complement. Okay. So in order to perform subtraction, we are going to go through a couple more steps, because we can perform addition, meaning if you have two 2-bit circuits, that circuit can actually multiply, as in, sorry, not multiply, can add voltages. Again, remember, it's in presence or absence of a voltage, right? So if 1 signifies is the presence of a voltage, 0 would signify absence of a voltage. So you can do 0 plus 0, which would give you 0, 0 plus 1, or 1 plus 0, but you can't take a subtraction. So if you're doing subtraction, like a mathematical operation, we implement it with this method, ones and twos complement. Okay. So what is ones complement? Ones complement, as the name suggests, you simply invert the entire number. If you have a number that is given by 0, 1, 0, 0, 1, 1, 0, 0, then the ones complement of that number is simply the complement, meaning every bit is inverted. 1, 1, 0, 0, 1, 1, 0, 1. Okay. When you implemented this in an electric circuit or an electronic circuit, 1 means the presence of voltage, right? So if you change the bias, let's say it's a transistor that's being applied, output of the transistor is high, meaning 1. If you invert the voltage of the input, then the output gets inverted, goes to 0. So implementing a complement in circuit is straightforward. Okay. Right now, I think when we first begin in the past, students always, and when I say a student, when I was a student, I had a hard time trying to figure out why are we doing this binary digital math and how does it tie to the circuits that we have done. So if we consider a transistor, one transistor which has an output, the output, if it has a high voltage, we say it's logic 1. If the output of the transistor is 0, then it's logic 0, low. So we can switch between 0 and 1 by simply controlling the input of the transistor. The output of the transistor can go to high voltage or low voltage. 1 can become 0, 0 can become 1 at the input. And so that is very easily implemented. And that process is known as ones complement. Now, twos complement simply means you add 1 to the least significant bit. So plus 1 to the least significant bit. If you add plus 1 to the least significant bit, what would you get? 1 plus 1 is 0, and carry would be 1. Yes. Yes. So here's the ones complement of the original number. The original number was 0, 1, 0, 0, 1, 1, 0, 0. This is the original number. The ones complement of that original number is 1, 0, 1, 1, 0, 0, 1, 1. And to find the twos complement, you add plus 1 to the LSB of ones complement. So then You have 1 plus 0. Sorry, 1 plus 1 gives you 0 and carry 1. Oh, not there. Sorry, here. Right? 1 plus 1 is 1, 0. So 0 and carry 1. Then 1 plus 0 plus 1 again gives you 0 and 1. 1 plus 1 again gives you 0 and 1. And again gives you 0 and 1. Wait, did I make a mistake anywhere? 1, 1, 1 plus 1, 0 and 1, 1, 1, 0, 1, 0, 0, 0. Oh, I'm adding the wrong number. Sorry. So 1 and 1, 1, 0, 0, 1, and 1, 0, 0, 0, and then 1, 1, 0, 1. Yes.
So in this case, we'd be subtracting 1 method, or
We're adding, well, right now we're just looking at ones and twos complement. Then we'll see how we can, yeah. Then I'll show you on the next slide. We'll do a small example. All right, so 1, 0, 1, 1, 0, 0, 1, 1, which is this number, is the ones complement. You add plus 1 to that ones complement, and you obtain 1, 0, 1, 1, 0, 1, 0, 0. That's the twos complement. So this is the twos complement, which is what we have here. Okay. Does that make sense? Take the original number, you invert all the digits, you get the ones complement. If you add plus 1 to the ones complement, you get the twos complement. Another way of directly writing the twos complement is basically you take the number, right? This is the original number. Original number. And you copy the number beginning from the least significant bit. So you write down 0, 0, which is the least significant bit. Here, let me show you this way. The original number is 0, 1, 0, 0, 1, 1, 0, 0. So if I wanted to write the twos complement, this is how I would do it. I would copy the least significant bit, write down 0, copy the next one, write down 0. Then I would copy the third one. You'd keep doing that until the first one is copied down. Once the first one is copied down, you copy the rest by flipping them. So 1 becomes 0, 0 becomes 1, this becomes 1, this becomes 0, this becomes 1. And that gives you the twos complement directly. And that is what is shown here. You copy the number directly, and then here you flip or invert. And that gives you the same answer. Okay. But now let me show you why we do this. Remember, I stated we want to perform subtraction, but we cannot perform a direct subtraction by implementing it in a circuit. But the circuit can do addition, but it cannot do subtraction. Okay. So we use these methods to actually perform mathematical operations. So let's say we wanted to do or perform 29 minus 27 in decimal. So 29 decimal minus 27 decimal, what would you get? So one person knows the answer. 2. All right, so in binary, 2910 becomes 0001 1101. That's in binary. And 27 is 0001 1011. Okay. If I was to perform this subtraction, binary, I want to subtract 27 from 29. Okay. So 29 in an 8-bit system would have 8 transistors. Let's say one transistor is enough, which is not, but let's just say one transistor is enough. So there are 8 transistors. The output of those 8 transistors are arranged so you get 0001 1101. Okay. That would mean it's 29. We understand it's 29. Transistors themselves are just on and off, right? Then we want to subtract 27 from 29, meaning the output of those transistors should give us 2, which is 00000001 or 10 at the end, right? All transistors are off except for 1. So the answer should be 2. But it cannot perform this directly. So we're going to use 2's complement method. And the way it works is we find the 2's complement of 27 and we add it to 29. And the result would give us 2 or decimal 2. Okay. So 2's complement of 27. So the answer would be determine. And I'm going for the shortcut. 2's of 27 and add to 29. Again, as I said, we can perform addition, but we cannot perform subtraction. So 2's complement of 27, we can find it directly by just copying down the number. Let's just do it both ways. So I'll do it on this side. So we have 0001 1011. Well, the first digit itself is a 1. So if I copy it down, I need to flip everything. So I should get, let's see, 100001. I copy this down, so I get 1. And then I flip the rest. So I get 0, 1, 0, 0, 1, 1, 1. Right? That's direct copy. The second method shown above. The first method would be this. 0, 1, 1. This is 27. 1's complement would be 1, 1, 1, 0, 0, 1, 0, 0. And then plus 1 gives me the 2's complement. That becomes 1, 0, 1, 0, 0, 1, 1, 1. Same number, both methods. 1, 1, 1, 0, 0, 1, 0, 1. Now you take that 2's complement and add it to 29. 29 is 0, 0, 0, 1, 1, 1, 0, 1. And 2's complement of 27 would be 1, 1, 1, 0, 0, 1, 0, 1. Okay. And when I add it, what happens? 1 plus 1, least significant bit, gives me 0 and carry of 1. That 1 comes down, gives me 1. This becomes 0, carry of 1. 1 plus 1 again gives me 0, carry of 1. Again, 0, carry of 1, 0, carry of 1, 0, carry of 1, 0, carry of 1. This right there at the end is discarded because we are 8 bits. We need 8 bits from the LSB, starting from the LSB to the MSB. This gives us 1, 0, which is 2. Okay, you can try any number as you want for practice. The method will work. Okay. Again, the recap, brief recap, is that we cannot perform direct subtraction using, using our electronic circuits or electric circuits. However, we can perform addition. And so we use addition methods. We can easily invert the output of a transistor. So we can create a complement. That first complement is known as singles or ones complement, where you invert every single bit. Zeros get converted to 1, ones get converted to 0. Then we have twos complement, where we add +1 to the least significant bit of the ones complement. There are 2 methods or 2 ways to find the twos complement. Once you have the twos complement, you simply add it to 29. The result is basically a subtraction of 29 and 27. Okay, yes. Depends on the use case scenario. For subtraction method, we need the twos complement. When we get to logic gates, we'll see how we can actually invert it. So this is just a technique or a method. Going forward, we're going to look at the circuits, the actual circuits that can actually convert or implement this logic. How can we convert from 0 to 1 and 1 to 0? Okay. All right, so we'll end class here today and we'll pick up here on Wednesday.
Thank you.
Mm-hmm.